So today I'm presenting our work, Machine Learning Models That Remember Too Much. It's a joint work with Thomas Ristenpart and Vitaly Shmetikov from Cornell Tech. So as an overview, we first propose a new threat model in machine learning. The scenario is a client who is not an expert in machine learning will train a model with adversary-provided training code. Training code is in the black box. So to make sure the black box is secure, clients will run the training code in an isolated environment. So during training, no information can be leaked. After training is finished, client may make the model available for others to use. For example, deploy the model in some applications. Adversary can then gain access to the resulting model. We then propose several attacks in this threat model. Basically, we're going to provide training code so that the model can learn two tasks at the same time. The primary task is what client wants, which is to let the model have a high predictive power so that client will happy to make the model available for others. The malicious task is to let the model leak the training data. So once the model is available, adversary can extract information about training data from the model. So our experiments will basically show that machine learning models can do well on both tasks simultaneously. Just to back off a little bit and give you some background information on machine learning. So machine learning has been successfully applied in many real-world systems. And to build such a system, we first need to collect some training data. The training data is a collection of XY pair, where X is the input feature vector, for example, an image of a face, and Y is the class label, for example, the identity of the face. And with the training data, we can train a machine learning model, which is a function that maps the feature vector to a prediction for the class label. The function usually has a set of parameters data to be learned during training. Once the training is finished, we can deploy the model for application or publish the model for others to use. So since machine learning is so popular, people from all kinds of backgrounds want to perform ML tasks on their data sets. And these people are not necessarily experts in machine learning. So for them to build a model, what kind of option do they have? Well, the first option is to go to these machine learning libraries. So Keras and Scikit-learn are probably the two most popular libraries out there. And these libraries basically provide extremely easy to use function calls that allow clients to train a machine learning model in just a few lines of code. Client does not need to know any details about the training algorithm or the implementations. They can just use the code as is. And most clients will not further investigating what the code is actually doing. Another option for clients is to go to these machine learning as service platforms. So companies like Google, Amazon, BigML all provide this simple training API that allow clients to upload their data to the cloud, and the platform is going to train the model for the client. The training in this case is a black box. So there is no way for client to know what exactly is the training code, the implementation. Sometimes client doesn't even know what kind of training algorithm is used. So what exactly is the training procedure? It's going to be a pipeline like this. So we start with client's data. We split the data into training set and test set. Training set can go through a data augmentation algorithm where we expand the training data. Data can be then fed into a training algorithm where we define the model and find the optimal set of parameters. We can also add a regularization to penalize the model parameters if it's too complex. Once we have a model, we need to validate the model, which is to see if the model performs well on the held out test data. And if the test performance is good enough, we output the model. Otherwise, we reject the model. The central part here is the detailed implementation of the training algorithm, which is going to be provided by a machine learning library or service provider. And this part is usually a black box for most clients, especially non-experts. So clients' data sets can be highly sensitive for some tasks. And if the training code is a black box, we really need to treat the code as untrusted because we don't know if the code is going to leak data in some way. And people have been trying to make the black box secure. One potential solution is to isolate the training environment. So isolated training environments can preserve data privacy when running untrusted training code. So in academia, there are systems with software-based isolation or hardware-based isolation. Basically, these systems provide isolation so that adversary cannot directly communicate or observe the training environment. So during training, no information can be leaked, and thus the training code can be untrusted. And in practice, Algorithmia is an example of such a platform. So basically, Algorithmia allows clients to train a model with third-party provided training code. The code can be closed-sourced, so it's a black box. And the training code can specify whether it needs an internet access or not. And if the training code needs internet access, Algorithmia will warn the user about a potential leakage of your data. And if it doesn't need, Algorithmia can isolate the training environments by cutting off the network access. So far, training environment can be secured by these isolated environments. After training is finished, and if the client is happy with the model, he might make the model available. For example, deploy the model for applications or provide a prediction API for others to query. So essentially, after training, data is gone, and only the model can be accessible by others. So now we have enough to motivate our threat model. And the scenario is client will train the model with adversary-provided training code in a secure and isolated environment. So during training, no information can be leaked. After training is finished, and if the model passes validation, adversary can then gain access to the resulting model. So the main question of our work is, what attacks arise in this threat model? So notice that test performance is actually the only criterion clients have to decide whether to make the model available or not. Okay? One thing client might not ask is, what else did the model capture about my training data? So basically, our attacks is going to focus on the what else part. What we're going to do is to provide training code to learn a model such that the model can do two tasks simultaneously. The primary task is to let the model have a good test performance. Then client will be happy to make the model available for others. And the malicious task is to let the model leak the training data. So when the model is available, adversary can extract information from the model. So there are two kinds of access adversary can get once the model is available. The first kind is Whitebox access, where clients fully disclose the model and adversary can inspect every parameters in the model. Another kind is Blackbox access, where clients only provide a prediction API. Adversary can send queries and see the outputs from the model. So for the Whitebox case, we're going to have attacks that leak the data through model's parameters. It's going to be either through the least significant bits of the model parameters, or through correlated parameters, or through the signs of model parameters. For the Blackbox case, we're going to leak the data through model's predictions. We're going to let the model memorize an extra malicious data set that encodes information about the training data. So for the purpose of this talk, we're going to only focus on attacks against the deep learning models. We also show our attacks generalized to other machine learning models in the papers. So let's start with Whitebox attacks. The very first thing we tried is least significant bits encoding, which is simply dump data into the LSB of binarily trained models' parameters. So model parameters are usually floating point numbers, and the lower bits are used to control the precision, are not that important to get the high performance machine learning model. So we can use the lower bits to encode data. So it's a very simple and effective attack. So to save time for other attacks, we're going to skip the detailed results, and you can refer to the paper if you're interested. So essentially, you want a more natural way of encoding. For example, encode the secrets in data during training. So let's see what does training do. Training basically tries to find the optimal set of parameters so that the model makes minimum mistakes. So essentially, it's a minimization problem. All we have to do is just to provide an objective function. And what people do is just use the loss function, which gives a penalty to each round prediction the model makes. And sometimes you can add a regularization term to constrain the model parameters. So once the objective function is defined, we can just apply any appropriate solver to find the optimal theta. So if we also want to encode the secrets in theta during training, all we have to do is actually just to express the malicious goal of encoding secrets as the term mathematically and add the term to the objective function. So the solver is going to take the two terms, the loss and the malicious term, and jointly optimize them. And the resulting theta is going to achieve the two goals at the same time. So our term will basically look like a regularization term. Okay. So standard machine learning uses regularization term to constrain theta. For example, if you want theta to be more sparse, you add L1 regularization. If you want theta to be small, you add L2 regularization. In our case, we want theta to encode the secrets. We add an engineered term to bias theta to encode the secrets about the training data. The first term here is for correlated value encoding. So correlation can leak data because it's a linear relationship. What we're going to do is to extract a sequence of real numbers as the secrets from the training data. For example, a sequence of pixel values for image data, and then just maximize the correlation between the secrets and the theta. The term here is going to be the negative absolute value of the correlation coefficients. So minimize the negative value will in turn maximize the correlation. The second term we have is for sign encoding. Each sign of model parameter can leak 1 bit information. So what we have to do is to extract the bit string from the training data, for example, the bit representation of your raw data, and convert the bit string into plus minus 1, so it's a sign, and just match the secret signs with the sign of model parameters. The term here is going to be a penalty term for the mismatch between the signs. So minimize the penalty, we'll try to match as much signs as possible. So once the model is trained and is published to adversary can decode the secrets by looking at the model parameters. Okay. For correlation, we can just apply a linear transformation to the parameters. For sign decoding, we just need to read the signs and convert it back to a bit string. So let's see the results on the Whitebox attacks. We're going to evaluate our attacks based on 2 metrics. The first one is the test performance, and also compared to a baseline test performance with the binarily trained model. The second one is the encoding quality, basically how accurate can we extract the training data from the model parameters. So we evaluate our attacks on several benchmark image classification data sets, and the difference to the baseline performance is shown in delta. As you can see, the difference are relatively small. Almost all of them are below 0.6%. In that way, client will be happy with the model and make the model available. As for encoding quality, we show some examples of reconstructed images from the model parameters. So the second row and the third row here are the reconstructed ones from the 2 encoding methods. So you can see there are some noises in the reconstructed images, but they are still very close to the ground truth. And they are all recognizable faces. So basically, we can accurately extract training data from the model parameters. So let's move on to black box attacks. So white box attacks require client to fully disclose the model, which might not always be the case, because client might only provide a prediction API. So we really need a way to leak data through the predictions, which is our capacity abuse attack. And this attack is motivated from a recent finding in deep learning, which basically says deep learning models can memorize randomly labeled data perfectly well. So if you query the model with your training data, it's going to give you back the exactly randomly assigned label back, even though the label does not make any sense at all. So this makes us think, what about memorizing extra malicious data that encodes the secrets in the labels? So basically, our attacks will make use of data augmentation. Data augmentation is a widely used technique in machine learning, especially computer vision tasks. For example, you can add rotations or scaling or distortion to an image, and these extra images can help the model generalize better. So what we're going to do here is to provide a malicious data augmentation algorithm that generates extra malicious data, encodes the secrets in its labels. The label can leak 1 bit information for a binary classification task. And then we're going to abuse the model's capacity by letting the model feed on both the original training data as well as the malicious data. So once the model is trained, adversary can query the model with the exact same feature vectors in the malicious data. And the prediction is going to get back is going to be close to the labels if the model memorizes well on the malicious dataset. So let's look at more details on the data augmentation part. We're going to first extract the bit string from the training data, for example, the bit representation of the pixel values. And for each bit, we're going to create an XY pair. The feature vector S is going to be a synthetic data generated deterministically. The label Y is going to be the secret bit we're trying to encode. So essentially, the malicious data set is equivalent to a synthetic input with randomly assigned labels. And hopefully, deep learning model should be able to fit this kind of data. And once the model is trained, adversary can regenerate the exact same feature vectors in the malicious dataset because the generation is deterministic, and just query the model with these feature vectors. Okay? The queried result are going to be the secret bit string we extracted with some arrow. Again, the arrow should be small if the model memorizes well on the malicious data. Let's see the results on the black box attack. Again, you can see the test performance and the difference to the baseline are very small, as shown by the delta. In that way, client will be happy to provide a prediction API for others to query. As for the encoding quality, we can see the reconstructed images are very close to the ground truth, which basically means the model definitely memorizes well on these malicious datasets. So to further demonstrate why the deep learning models perform so well, we here have a visualization of the features that the model learned on CIFAR10 datasets. The features are in high dimensional, so we project it into 2D using t-SNE projection. And the color indicates the class label. The solid points here are the features from the test data. So as you can see, the points with the same color forms a cluster, which means the model learned the right feature to distinguish between classes. And that's what clients cares about. So what about the malicious datasets? Turns out they actually just live on the boundaries of the test datasets. So for both hollow points and solid points, the points with the same color still forms a giant cluster, but there's a gap between them. And that basically means the model has learned the feature to classify both types of data correctly, even though their distributions are very different. So one type of data is the real images with correct labels. The malicious data are synthetic images with randomly assigned labels. So here's a summary of our attacks. Basically, what we did is to provide training code to let the model learn two tasks simultaneously. The primary task is what clients want, which is let the model have a good performance. The malicious task is to let the model leak training data. And for Whitebox attacks, we provide a standard objective function to perform the primary task. And we also add an engineer term to bias data to encode the secrets to do the malicious task. For the black box case, we let the model feed on the client's data to do the primary task. We also let the model memorize an extra data set that encodes the secrets to do the malicious task. And it turned out machine learning has no problem of doing well on both tasks simultaneously. So countermeasures. So one interesting measure might be to look at the difference in the parameter distributions of a binarily trained model as well as model trained by our attacks. So here are the histograms of the distributions of parameters for three encoding methods. The ones in the greens are the distribution for our attacks. As you can see, there are some differences for correlated value encoding and sign encoding because we add an engineered term to bias the model parameters. And as for capacity abuse attack, the two distributions are basically identical. And one important thing here is, in order to tell the difference, one has to understand what is the normal parameter distributions for a binarily trained model. So takeaways. As we have seen, if the training code is untrusted, even isolated systems cannot prevent leakage because model can essentially perform well on primary tasks and learn other things at the same time. So ML code should not be applied blindly to sensitive data sets. We should understand the code and make sure the model only doing what it's asked to do. Thank you for listening. The code is available online also. Now I can take questions.
So based on the results, it looks like the models that you were using were over-provisioned for the machine, for the benign tasks that the model was being asked to perform. Did you look at, typically people use techniques like pruning and low precision weights to make sure that the models are not heavily over-provisioned. So did you look to see what happens to the success of the malicious attacker when the model is pruned and represented using low precision weights?
So by pruning, you mean?
So for instance, a lot of pruning techniques will, dramatically reduce the size of the network.
Oh, I see.
Right. And that makes sure that the network is now appropriately provisioned in terms of its learning capacity to the actual benign task.
Yeah. So actually for so make the parameters lower precision. Is that what you mean?
Or sparser, yeah.
Yeah. For sparsity, we didn't look into that. For lower precision, I think for the Whitebox case, the precision does not affect the signs, right? So for sign encoding, it should still work. As for correlation encoding, I think if the parameter has lower precision, the correlation relationship can still be captured. As for Blackbox case, I don't have a good hinge on that. Maybe it's interesting countermeasures to see.
Okay, thank you.
I have a clarification question.
Yeah.
So it wasn't clear to me how much of the sensitive data you are leaking at the end. Like how many data points are you leaking?
Yeah, so the detailed results are in the paper. What we can say is it depends on the size of the model. So if for deep learning models with like millions of parameters, it can leak a significant amount of data. But the detailed numbers are given in the paper.
I had a question about reconstructed images. First of all, how much is the computation required to do the reconstruction? And have you tried using the reconstructed images as test data, and what was the result for that?
The computation should be very simple, because for Whitebox case, you just need to do some simple, like for correlation, we just need to do some simple linear transformation. And for signs, it's just like convert the bit stream back to the pixel values. And as for the Blackbox case, we indeed need to query all the malicious data sets we encoded. That depends on the malicious data, the amount of malicious data we added. Okay. As for the second question, did we use the malicious data, the reconstructed image, as the test data?
Yes.
And no, we didn't try that, but we showed that qualitatively they are really close to the ground truth.
Okay, thanks. Let's thank our speaker again.